Okay, so this is for AQA Physics A-level specification. This is on topic 3.2, which is particles and radiation. It's on specification point 3.2.1.1. Okay, this is on constituents of the atom. So the first thing that you need to know is about atoms. Atoms come from the Greek word of atomos, meaning that they are very, very small, less than a millionth of a millimeter in diameter. We can see them with an electron microscope, but what we do know is that in the center they contain a positively charged neutron consisting of protons and neutrons, and that's in our nucleus of our atom. Each atom has a nucleus that consists of protons and neutrons. Around them they are orbited via electrons, which orbit at varying energy levels. Okay, so the electrons orbit around the nucleus. The word nucleon means particles which are protons and neutrons within the nucleus. Each electron has a negatively charged. Okay, and the nucleus is positive charged because there are no electrons in it. It's just it's simply just the protons and the neutrons. So what you need to know is about the SI units. SI units are the standard international units. You need to know them. That for charge, we have the coulomb, and for mass we have the kilogram. Okay, and we're going to apply that information to the following table. So the following table that I'm going to draw is going to consist of the 3 subatomic particles that you're required to know for the course, and details pertaining to each of them. So what we have is we have the proton. Let's start with the proton. The proton itself is positive charge. At GCSE you may have seen it have a relative charge of, we say, +1, but here we actually use the proper charge on it, and the proper charge on it is 1.6 times by 10 to the minus 19 coulombs. The mass of a proton is 1.67 times by 10 to the minus 27 kilograms. You need to remember these values, and you'll see why in a moment. Electrons, they are similar to protons. In this scenario, they have a minus 1.6 times by 10 to the minus 19 coulombs. So that's negative for the electrons. Their mass is slightly different. It's 9.11 times by 10 to the minus 31 kilograms. Really, really, really tiny mass. And finally, for the neutrons, they have a 0 charge, so they are not charged because they are neutrally charged, and their mass is the same as that of a proton, 1.67 times by 10 to the minus 27 kilograms. Okay, so that is for a neutron. All neutral atoms which have the same number of protons and electrons have an overall negatively charged, neutral charge. They have an overall neutral charge because they contain the same amount of protons as they do electrons. If a uncharged or if a neutral atom gains or loses electrons, then it becomes a charged atom. And what we call a charged atom is an ion. Okay? An ion is where we have a plus or minus. For example, if we had a neutral atom, say we had atom X, and it had 20 protons and 20 electrons, if I take away 2 electrons, it now has 18 electrons, and it has 2 more protons, and therefore we say that element X now has a 2 plus charge. Similarly, if we go back to our element X, 20 protons, 20 electrons. If I add 2 more electrons, so now it has 22 electrons, overall element X has a 2 minus charge. Okay. Isotopes. The definition of an isotope, and you need to know this, is it is a atom which has the same number of protons but a different number of neutrons. So if we talk about isotopes, we have lots of isotopes in everyday life. Chlorine has 2 isotopes, chlorine 35 and chlorine 37. And their abundance is chlorine 35 is 75% abundant, and chlorine 37 is 25% abundant. How do we use this information? If we want to calculate the relative atomic mass, what we do is we say that 75 times by 35, all in brackets, plus 37 times by 25 all in brackets, divide that by 100, and that will give us 35.5, which is what you see on the periodic table. So what we do is we take the abundance and we multiply it by the mass number, we add it to the product to the abundance and the mass number, and we divide it by the total abundance, which normally, if it's as a percentage, it will be 100, and that's how we calculate the relative atomic mass of isotopes. So just remember that formula. If I were to write out the formula, we know that it's the sum of the abundance multiplied by mass over the sum of the abundance. Okay, that's our formula there for relative atomic mass. So the kind of notation that we use for atoms in the specification point is we're going to use this notation X, and we're going to say that it has two numbers associated with it, A and Z, as you may see on the periodic table. A is what we would know as the mass number, okay, and that is the number of protons plus the number of neutrons. And Z is our atomic number, or our proton number, and that's just the mass of the protons, the charge of the protons, how many protons there are, or how many electrons there are, and X being the atomic symbol. So if I give you an example, oxygen, 16.8, this is Z, and this is going to be our A. This is the mass of the protons and the neutrons, and this is just the number of protons or the number of electrons, because we have a neutral atom over here. Last thing that we need to know about for this topic is that something called specific. Okay, so specific charge, what is it? Specific charge is the charge to mass ratio of any type of atom, element, anything like that. So if I want to calculate the specific charge of a proton, we take the charge of a proton, which is 1.6 times by 10 to the minus 19, and we would divide it by its mass, which is 1.67 times by 10 to the minus 27. A little bit of calculation, and that will give you the answer, whatever that is. So specific charge, if we had to kind of put it into a bit of context, what it can do is it can tell you the charge per unit mass of atoms, and what you will find is that electrons have the highest specific charge. Remember that we have charge over mass, which is coulombs over kg. If we write it, therefore we have the unit being coulombs per kilogram, like that. Okay, that's all we need to know for this specification point. The last thing is about the atomic mass unit, which is mentioned in the scheme of work. So the atomic mass unit, or AMU, is essentially a unit which is relative to 1/12 the mass of carbon-12. If you look up on chemistry, the definition of an MR is the mean mass relative to 1/12 the mass of carbon-12. That's just the same for the atomic mass unit. Okay, that's all for the spec point. Next we'll be going through 3.2.1.2, which is on stable and unstable nuclei. Thank you very much.